Welcome back. To get started where we left off, we will go into more detail the actual components that make a yield monitor work. We will start with the grain flow sensors. There's only a couple of ways to measure the volume of the grain passing through a combine in real time. The one pictured above is an impact type mass flow sensor. This concept was invented by Al Myers in the early 1990s and began to gain traction through the late 90s, allowing Al to invent the company AGRI and to have his design be one of the most widely used instantaneous yield monitoring systems. The way it works is clean grain is brought up from the bottom of the combine by a paddle chain to the hopper area where the grain drops into the last auger before entering the grain tank. During this handoff, the grain is thrown from the paddle chain against an impact plate. This measures either the force applied by the grain impacting the plate or the amount of displacement that occurs when the grain strikes the spring-loaded plate. Force is measured by the load cell. This is a device that converts the effect of a load acting on it into an electrical signal. The strain gauge is bonded to the load cell and is responsible for this conversion. When measuring the displacement, the potentiometer measures this movement of the impact plate to correlate a yield. Optical type volume flow sensor. Mounted in the clean grain conveyor, the optical type emits a light and a photosensor detects the degree to which a combine's clean grain elevator is loaded. Calibrations still have to be done to know the bulk density, which is the weight per unit volume of the harvested grain, to be able to calculate crop yields. This sensor then would send the signal to the display that will correlate it to a yield. This type is by Raven Industries and Trimble. Combines today are sold with one type of flow sensor or the other, depending on manufacturer, but older machines can be retrofitted to either type. Grain moisture. Is it important? At harvest, the farmer is concerned about preserving the quality of the grain. That means weighing the want to harvest dry grain for safe storage and the need to get the crop out of the field where it is vulnerable to the weather and other elements. The grain moisture will come into play as a farmer makes this decision. Crops can be harvested wet as long as it does not hamper with the threshing process. However, it costs money to dry the grain. Either the farmer or the elevator will run wet grain through a grain dryer, which uses propane or natural gas to heat up air being blown through the grain by giant fans, which will cost a producer a drying charge. Also, crop that is out in the field can dry down past the standard moisture. With the loss of the moisture, you lose weight, which is what the producer is paid upon, resulting in a loss of revenue from being too dry. The moisture of a crop is generally not uniform throughout the whole field and more than likely will vary a great deal across the different soil textures and topography of any particular field. Also, crops that mature later in the year tend to have a greater degree of variance between moistures throughout the field. So the moisture sensor, that is the key to any yield monitoring system, is needed to convert the yield data to a standard dry value in order to compare the yields throughout the field accurately. Also, this information can be very useful in planning the destination of certain truckloads. If a grower is in a wet area of the field, he or she might send that truck to a different location. So the grain moisture content must be measured on the go in an instantaneous yield monitor. It is generally located in the combine's clean grain system near the grain flow sensor. A capacitance type sensor is the one most often used to measure the grain moisture content. It can accumulate and hold an electrical charge on metal plates separated by a dielectric, which is a material that does not conduct electricity but can contain an electrical field. This then measures the dielectric properties of the grain that flows between the metal plates. As the dielectric properties of the grain increase, so does the dielectric constant, making the measurement equal to the moisture content of the grain. So far, the combine knows the weight or volume of the grain being harvested and can convert that to standard dry yield as soon as it knows the area being harvested. In order to accomplish this, the monitor, which is the brains in all this, needs to know the speed and the cutting width. Then it's just a formula that uses grain flow rate times the unit conversion factor divided by the cutting width times the ground speed. The cutting width portion of that is manually entered into the monitor and can be entered in the desired unit, example inches, feet, or number of rows. The ground speed is instantaneously gathered by the harvester and can be done a few different ways. A shaft speed sensor is a magnetic sensor that measures the rotational speed of the drive shaft from the combine's transmission and can then calculate that speed and relay it in real time to the monitor. Accurate speed data is very crucial to a good yield data. If the yield data is flawed or being poorly portrayed, it will show up in the final yield map. Also, erratic driving will cause the yield data to be skewed because there is only a small delay in the calculations. And if the combine speeds up real quick, it will cause a huge decrease in the yield, and if it suddenly slows down abruptly, there will be a few yield data points that will be recorded extremely too high. Radar and ultrasonic sensors are more accurate and more maintenance-free than shaft speed sensors. They use guns that direct a signal towards the ground. A radar system emits a microwave signal, and an ultrasonic system emits high-frequency sound waves. In either system, the signals reflect back to the sensor after hitting the ground. These devices will be mounted on the combine frame close to the ground. GPS-based measurement can also be used for speed input. It is being received by the receiver and portrayed through the monitor. Probably would not be the first choice to use for the yield data interpretation. If you have a GPS app on your phone, the next time you're riding with somebody through a town, pull out your phone and bring up that app. As you drive through town, constantly changing your speed with the flow of traffic, look at the speed being displayed on your phone in correlation with the speed being displayed on your vehicle's dash. You will notice a very distinguished delay. This delay in data on a combine's yield monitoring system will affect the yield being represented, throwing off the yield data. So, out of the shaft speed sensor, the radar sonar sensor, and the GPS speed sensor, the most accurate and maintenance-free would be the sonar radar sensor. While the combine is doing the calculations of the area it harvests by using one of the speed sensors, along with the entered width, it needs to know the difference between truly harvesting and driving around while unharvesting. This would include turning on the headlamps or driving to and from the truck. The combine's harvesting system would be running, but no crop would be entering. This would be the job of the header position sensor, to suspend counting while the header is in an elevated, non-harvesting position. When the header is lowered, the area counting will begin again. The sensitivity of this sensor can be adjusted so you are not counting acreage that you do not need to be. Yield monitoring software can allow the operator to specify an operation delay to account for the time it takes the grain to move from the header to the grain flow sensor. These delays would be classified as a start of pass delay and an end of pass delay. Start of pass delay allows the initial flow of the grain past the flow sensor into the combine to be ignored in the yield calculations. Similar to the start of pass delay, the end of pass delay permits grain flow that occurs after the header is lifted to be included in the yield data. All of these instantaneous data will be portrayed by the monitor in the combine cab. This is mounted in easy view of the operator, like shown in the slide. Information would be entered into the display to calibrate, record, and monitor the grain yield. This information would include the grower's name and field name. He can track a load name or a number and must enter the cutting width along with the crop being harvested. Once the monitor is calibrated, the monitor will display information such as instantaneous crop yield and the moisture. It will keep an average yield and the harvesting acreage. It will allow the producer to know his travel speed and will monitor the quality of the GPS signal received. There's a lot of components that must be working properly to accurately record yield data. But yield data can be recorded without the calibrations. Calibration is key to usefully analyze any yield data and must be performed by the owner-operator. The calibration methods will differ between the yield monitoring systems, but the calibration needs to correlate with the grain's density. If using a mass flow sensor, it needs to correlate a certain weight being pushed against the plates with the pounds hitting it. Some of the small details will differ between brands, but in them all, an operator must harvest a certain amount of grain and then unload the hopper into a carrier with a scale, or take the grain to a scale to ensure the correct calibration. Grain flow meters need to be calibrated or zeroed out to nullify the effects of the machine's vibration. Make sure that all the operator input data is correct and the monitor is set up with the correct units of weight and area. Calibration during harvest. If harvesting conditions are similar to those that existed when calibration was completed, the yield monitor will be highly accurate. However, if harvesting conditions vary greatly from when the calibration was completed, the accuracy of the yield estimates can suffer. Solution is to perform calibrations over a range of grain flow rates. If environmental conditions change crop conditions during harvest, recalibration might be needed. Moisture content estimates need to be calibrated by comparing the yield monitor's moisture sensor to sample test using an already calibrated moisture tester. All crops will need to go through this entire calibration process. For example, if you calibrated the combine for wheat and are now switching to soybeans, you must recalibrate your combine for soybeans and go through all these calibration steps again. Things to consider when out collecting yield data. On-the-go sensors can collect yield data every 1, 2, 3, or 5 seconds, depending on what the operator chooses. As the operator, you know this yield data is being logged very frequently, so pay attention to speed and try to harvest at a constant and consistent speed while maintaining a full header width. Try to avoid abrupt speed changes. Let the header switch do its job, so fully raise the header when not harvesting, so there is no irrelevant yield data points being logged. And remember to enter the correct information into the monitor. The monitor can store an extensive record of crop production information, to include the yield values for the season, farm, field, and load. A data storage device in the yield monitor can be removed to transfer data files to a home computer. It is recommended to always make a backup of the yield data. It probably does not need to be done on a daily basis, but if all the work has been done to gather accurate, useful yield data, treat it as valuable information and collect it from the monitor periodically and create a backup. Especially if you are going to clean the data, always have that copy of the raw data just in case. In the next video, we will discuss the yield maps.